Hey everyone, welcome back for another deep dive. Today we're going to be looking at something pretty cool. It's all about the forces that are at play between charged particles. And we'll also touch on how we can actually store electrical energy. And I think you'll be surprised by some of the real-world applications.
Yeah, it's really fascinating stuff. And you know what's particularly interesting to me is that inside a conductor, even if it's charged, the electric field is actually zero.
Wait, really?
Yeah.
That's kind of mind-blowing. When I think of a charged object, I imagine electric field lines radiating outwards from it. So how can the field inside be zero?
It all comes down to how those charges behave inside the conductor. They actually rearrange themselves in a way that cancels out the electric field within the material itself. But before we get too deep into that, let's start with a concept that's fundamental to understanding all of this. Conservative forces.
Okay, conservative forces. Back to Physics 101. I remember the term, but could you give us a refresher on what makes a force conservative?
Absolutely. Imagine for a moment that you're hiking up a steep mountain. You're carrying a heavy backpack, and it's taking a lot of effort, right? You're doing work against gravity.
Yeah, I can feel the burn in my legs just thinking about it.
But here's the thing. That work you're doing isn't just disappearing. It's being stored as potential energy, ready to be released if you were to, say, accidentally drop your backpack.
Oh, I see. So it's like winding up a toy car. You put in the energy, and then the car can use that stored energy to move.
Exactly. And electrostatic forces, just like gravity, are also conservative forces. When you move a charge against an electric field, you're doing work, and that work gets stored as electrostatic potential energy.
So that's where the idea of potential comes in. It's about stored energy, the potential for that energy to be released and do something.
Precisely. Now imagine, instead of a heavy backpack, you're moving a tiny positive charge within an electric field. The electrostatic potential at a certain point tells us how much potential energy that charge would have at that location.
Okay, so it's a way to quantify the potential energy at different points in the field. But I also remember learning that what really matters is the difference in potential between 2 points, not the absolute potential at a single point.
Absolutely. You're spot on. Think of it like this. Saying that a mountain peak is 10,000 feet high is useful information, but for someone climbing that mountain, what really matters is the difference in elevation between their starting point and the summit.
Right. It's the change in height that determines how much work the climber has to do.
Exactly. And in the same way, the difference in electrostatic potential between 2 points in an electric field tells us how much work is needed to move a charge between those points.
So it's all relative. To make calculations easier, we typically set the potential at an infinitely distant point to be zero.
You got it. It's like choosing a reference point, like sea level, for measuring altitude.
That makes sense.
Yeah.
So how does this idea of potential play out when we're dealing with different types of charge arrangements? Let's start with something simple. A single point charge.
Okay, imagine a single positive charge just hanging out in space. The electrostatic potential around that charge would decrease as you move further away from it. Think of it like the heat from a campfire.
The closer you are, the more intense the heat.
Yeah.
And as you move further away, it gradually fades.
Exactly. And just like with the campfire, the potential from a point charge gets weaker as you move further away. And if the charge were negative instead of positive, the potential would also be negative.
So the sign of the charge determines the sign of the potential. That makes sense. Now, things get a bit more complex when we start talking about electric dipoles. Can you remind us what those are?
Sure. A dipole is basically just two opposite charges separated by a small distance. You can think of it like a tiny little battery with a positive and a negative terminal.
Right. And I remember learning that the electric field around a dipole is quite different from the field around a single point charge. Is the potential also different?
It is. The potential due to a dipole depends not only on how far away you are from it, but also on your orientation relative to the dipole's axis.
So it's not just about distance, but also about your angle relative to the dipole. That adds another layer of complexity.
It does.
Yeah.
But even when things get more complex, like when we have a whole bunch of charges all over the place, there's a principle that helps us make sense of it all. It's called the superposition principle.
The superposition principle. I'm intrigued. Tell me more.
Basically, the superposition principle tells us that the total potential at a point due to a group of charges is simply the sum of the potentials due to each individual charge. It's like having a bunch of lamps scattered around a room. The total brightness at any given spot is just the sum of the brightness contributions from each lamp.
So it's like each charge creates its own little potential bubble, and the overall potential at a point is just a combination of all those bubbles?
That's a great way to picture it. It's a very powerful concept that allows us to analyze complex charge distributions and understand their overall effect. Now, speaking of visualizing electric fields and potentials, have you ever heard of equipotential surfaces?
Equipotential surfaces. Yeah, I remember vaguely coming across them in my physics textbook. What's so special about them?
Equipotential surfaces are like contour lines on a topographic map. They connect points that have the same electrostatic potential.
Ah, I see. So if you were to move a charge along an equipotential surface, you wouldn't have to do any work because the potential is constant along that surface.
Exactly. It's like walking on a flat path on a hillside. You're not changing your altitude, so gravity isn't doing any work on you.
That's a helpful analogy. And how are these equipotential surfaces related to the electric field lines?
They always cross each other at right angles.
So if you were a tiny charged particle following an electric field line, you would always be crossing those equipotential surfaces perpendicularly.
Precisely. And that relationship between field lines and equipotential surfaces gives us a really powerful visual way to understand how charges behave in different regions of space.
This is fascinating stuff.
Yeah.
It's amazing to see how these seemingly simple concepts can reveal so much about the behavior of electric charges. But now, I'm really curious about that mind-boggling idea you mentioned earlier about the electric field being zero inside a conductor, even if it's charged.
Ah, yes, electrostatic shielding. It might seem counterintuitive, but it's one of the most striking consequences of how charges behave in conductors.
I'm all ears. Explain it to me like I'm 5.
All right, picture a hollow metal sphere. Now, imagine we dump a whole bunch of charge onto that sphere. What do you think happens?
Well, I would guess that the charge would spread out evenly over the surface of the sphere, and there would be an electric field radiating outward from the sphere.
That's a very reasonable assumption. And for a non-conductor, that's exactly what would happen. But for a conductor, something truly remarkable occurs. Because the charges are free to move within the conductor, they rearrange themselves in a way that completely cancels out the electric field inside the sphere.
Whoa, wait a minute. So you're saying that even though there's all this charge on the surface, the electric field inside is actually zero? That's kind of mind-blowing. How does that even work?
It's all about equilibrium. The charges on the surface repel each other, and they keep moving around until they find a configuration where the net force on each charge is zero. This configuration results in no electric field inside the conductor.
So it's like the charges on the surface form a kind of protective barrier, shielding the interior from any external electric field.
That's a great way to think about it. It's called electrostatic shielding, and it has some really important practical applications.
I bet. This is really opening my eyes to the hidden complexities of what I thought was a simple concept. I'm eager to learn more. What else can you tell us about electrostatic shielding and its applications in the real world?
Well, one of the most common examples is in protecting sensitive electronic equipment from electromagnetic interference. But before we dive into that, let's switch gears a bit and talk about another important player in the world of electrostatics: dielectrics.
Dielectrics. Those are insulators, right?
Yeah.
I'm curious to see how they fit into all of this. Lead the way.
Exactly. Dielectrics are insulators, which means they don't have those free charges roaming around like you find in a conductor. But that doesn't mean they're just sitting there passively.
So how do these seemingly quiet dielectrics get involved in the exciting world of capacitors?
Let's think about what happens when you apply an electric field to a dielectric material. Okay. Now, even though the molecules in the dielectric are neutral overall, the positive and negative charges within each molecule get slightly shifted.
Ah, so it's like each molecule becomes a tiny little electric dipole aligning itself with the electric field.
Precisely.
Yeah.
And here's where things get really interesting. This alignment of all these molecular dipoles actually creates its own electric field inside the dielectric. But here's the kicker. This new electric field is in the opposite direction to the original applied field.
So it's like the dielectric is kind of pushing back against the electric field, trying to weaken it.
That's a great way to put it. And this pushback effectively reduces the overall electric field strength inside the capacitor.
Okay, I'm starting to see how this all ties back to capacitance. We know that capacitance tells us how much charge a capacitor can store at a given voltage. So how does weakening the electric field affect that storage capacity?
Well, remember that voltage is essentially a measure of the work done per unit charge to move it across an electric field. So if the electric field strength is reduced, the voltage across the capacitor plates also goes down for the same amount of charge.
And since capacitance is charge divided by voltage, If the voltage decreases for the same amount of charge, the capacitance must increase.
You got it. By introducing a dielectric, we've actually boosted the capacitor's ability to store charge at a given voltage.
It's like the dielectric is giving the capacitor a little helping hand, letting it hold more charge without needing as much electrical pressure.
Yeah.
But I'm guessing not all dielectrics are created equal, are they?
You're right about that. Different dielectric materials have different abilities to polarize, which means they'll have varying impacts on capacitance. This ability is measured by something called the dielectric constant, which tells you how much the capacitance increases compared to having a vacuum between those capacitor plates.
So a higher dielectric constant means a bigger boost in capacitance. It seems like choosing the right dielectric is a crucial step when you're designing a capacitor for a specific purpose.
Absolutely. If you need a capacitor with a really high storage capacity, you'll want to choose a dielectric material with a high dielectric constant.
This is fascinating. It's like there's this whole hidden world inside a capacitor with these tiny molecular dipoles all lining up and influencing how much energy can be stored. But where exactly is all that stored energy in a capacitor? I remember learning something about energy being stored in the electric field, but I'm not sure I ever fully grasped what that meant.
It's a great question. Think about it this way. When you stretch a rubber band, you're putting energy into it, right? And that energy is stored in the stretched rubber band, ready to be released when you let go. In a similar way, the energy stored in a capacitor actually resides in the electric field between the plates.
So the electric field itself is acting like a reservoir of energy, waiting to be released. And I'm guessing the amount of energy stored depends on both the capacitance and the voltage.
Exactly. The higher the capacitance and the higher the voltage, the more energy is stored in that electric field. It's like stretching a stronger rubber band or pulling it back further. You can store a lot more potential energy.
This is really making me appreciate the power and elegance of these fundamental concepts of electrostatics. It's amazing how something as seemingly simple as two metal plates and an insulator can have such a profound ability to store and release energy.
It's a testament to the brilliance of the physicists and engineers who have figured out how to harness these principles to create all the devices that power our modern world. But the story of electrostatics doesn't stop there. Let's explore what happens when we start connecting multiple capacitors together.
Connecting capacitors. It sounds like we're stepping into the world of circuits. It's like building pathways for electrical energy to flow and be stored.
That's a great way to visualize it. And there are two fundamental ways to combine capacitors: series and parallel. Each configuration has its own unique properties, and it affects the overall capacitance and energy storage of the system.
Okay, I'm all ears. Let's dive into these different configurations and see how they change the way capacitors behave.
So we have these two ways to hook up capacitors: series and parallel. It's like we're setting up an electrical obstacle course for the charges to navigate.
I like that analogy.
Yeah.
So tell me, what's going on in a series connection? How are those capacitors arranged?
Well, in a series connection, you've got your capacitors connected end to end, like links in a chain. So the same amount of charge has to flow through each capacitor in the line.
So it's like a single file line of charges, all trying to squeeze through each capacitor in turn.
You got it. But here's the thing. Even though the charge is the same across all those capacitors, the voltage across each one can be different. Depending on its capacitance. Think of it like a series of waterfalls.
Okay, I see where you're going with this. The same amount of water flows through each waterfall, but the height of each waterfall can be different.
Precisely. And when we connect capacitors in series, it actually reduces the overall capacitance of the system.
Really? So it's not as simple as just adding up the capacitance of each individual capacitor?
Nope. Each capacitor in that series chain is adding a bit of resistance to the flow of charge. So the total capacitance of the series combination ends up being less than the capacitance of any individual capacitor in the chain.
Interesting. So if you needed a capacitor with a lower capacitance than you had on hand, you could actually create one by connecting multiple capacitors in series.
Exactly. Now let's flip the script and talk about parallel connections. In this setup, our capacitors are connected side by side, like lanes on a highway.
Oh, I see. So it's like those charges have multiple paths they can choose from, and each path has the same electrical pressure pushing them along.
That's a great way to think about it. And unlike in a series connection, the voltage is the same across all the capacitors in parallel. But the charge on each capacitor can be different depending on its capacitance.
Okay, so how does this parallel arrangement affect the overall capacitance?
Connecting capacitors in parallel actually increases the overall capacitance. You're essentially providing more storage space for those charges. The total capacitance is just the sum of the capacitances of all the individual capacitors.
So it's like combining a bunch of smaller storage units into one giant warehouse. If you needed a capacitor with a larger capacitance, you could just connect several smaller ones in parallel.
You got it. Now, all of this talk about capacitance and energy storage leads us to one of the most exciting frontiers in this field, supercapacitors.
Supercapacitors, that sounds pretty high-tech.
Yeah.
What are they and what makes them so special?
Supercapacitors are like capacitors on steroids. They use cutting-edge materials and clever designs to achieve much higher energy densities than regular capacitors.
So they can store a lot more energy in the same amount of space.
Thanks.
That's incredible. But I imagine there must be some challenges in developing these supercapacitors.
Absolutely. One of the biggest hurdles is finding materials that can withstand the incredibly high electric fields that are needed for supercapacitors to store all that energy. And then there's the challenge of designing electrodes with massive surface areas to maximize the amount of charge they can hold.
It sounds like it requires a delicate dance between material science, engineering at the nanoscale, and some seriously creative design thinking. But the potential benefits seem enormous.
Oh, without a doubt. Supercapacitors have the potential to revolutionize so many things, from how we power our vehicles to how we store energy from renewable sources. And that's just scratching the surface.
This has been an amazing journey into the world of electrostatics.
Yeah.
We've covered so much ground, from the basics of potential energy to the intricacies of capacitors and the mind-blowing possibilities of supercapacitors.
It's truly remarkable how these invisible forces play such a fundamental role in shaping our world.
Well, folks, there you have it. A deep dive into the fascinating realm of electrostatics. We hope you've enjoyed exploring these powerful concepts with us.
And until next time, keep those minds charged up and never stop exploring the wonders of science.